Hi everybody. So today we're going to talk about multiple input data sets, and we're going to talk about these in three parts because it's kind of an involved topic, and so we're going to break it down into three videos. In the first part, we're going to talk about how we can generate a calibration curve when we look at a multiple input data set, in order to calibrate an instrument that we might want to use to take some measurements. And then in part two, we're going to look at an example of that process. And then in part three, we're going to look at, okay, so we went through this calibration process, but we know that there's some error or there's some uncertainty involved in doing that, and how can we quantify that uncertainty so that we can bring it into our design process and know exactly what sort of uncertainties we're dealing with so that we know exactly how much stock we can put in certain measurements. So first, types of calibration. First we have this, what we call a static calibration. So this is a calibration that's not a function of time. So we look at maybe the voltage response of a pressure transducer, and we calibrate with given pressures, and we look at those output voltages, and we create a calibration curve, and that calibration curve stays the same calibration curve no matter what. And then we have dynamic calibration. So this is where in our calibration we're actually looking at the response versus time of a known type of input. So that input can be sort of an impulse response, where you send a short, quick pulse of information, and then you look at typically, let's say, the voltage response of your sensor, or a step function, where you have no input, and then all of a sudden your input goes from 0 to 1, and then you look at how your sensor actually responds, so that you can get an idea of how it responds to those different inputs and calibrate what the time response, what the input signal would be based on the time response that you actually see in your sensor. And then we're going to talk about sequential calibration. So this is when we march through our known calibration inputs in one direction, either up or down. And then a random calibration is when, we may want to calibrate some instrument over a certain range, and we're going to input all over that range randomly so that we don't introduce, or so that we reduce the effects of any types of hysteresis that we might see. And I think we'll talk about hysteresis in the next kind of video. So what is calibration? So if we have a measurement system that measures some variable, how do we know how the output changes as that variable changes? What's the error in that process? And we often want to look at, is that relationship linear or is it not linear? What type of function are we going to use to fit our data? The reason we use functions to fit our calibration data is because generally we can take that function with us anywhere, and it's really easy to express, rather than, say, interpolate off of some table of data points that we took during our calibration. And then, how do we get that conversion function between our output and our measured value? So calibration in general is the process by which we compare the response of an instrument to our data input over some range. And it's important to note that we need to calibrate over the range that we expect to see in the use of our instrument. We don't want to calibrate in a certain range of inputs and then put our sensor into the field and be measuring inputs that are wildly different than the range over which we calibrated. If the input is known and the output is measured, then we can ask all of these, we can answer all of these above questions in a quantitative way. So what does the calibration curve generally look like? So in general, we have some input X and some output Y, and we plot these blue data points where we input our X values and we measure what we get out on the Y. And then you can see, this was done in Excel, and so in Excel it's rather simple to fit some, quadratic formula to this data set. And then we get this R squared value, which we'll talk about a little later, but it gives us some idea of how well that curve predicts the data points. So how far those data points lie on average sort of from that curve. We can also have calibration curves that come out quite linear. So here we get 10x plus 0.02. We see the R squared value very high in this instance because those data points, I should say it's very close to 1, which means that we don't have any deviation from the calibration curve. And so since that R squared value is very, very high, it tells us that on average our data points lie very close to our calibration curve. So this is some other terminology. I think these slides will get posted so you can go back and look through these. But so our static sensitivity is how much change in input generates a specific amount of change in the output. So that's how sensitive our output values are to our various changes in input. Our true values are known inputs. That's what we are comparing to. So if we're calibrating a scale, that's the weights that we put on the scale. We know this is a 10-gram weight. We know this is a 100-gram weight. We know this is a 1 kilogram weight. Then we have our absolute error. Our absolute error is the difference between the output that we measured and the input that we knew, our true value. Our relative error is that absolute error value divided by the true value. And then the accuracy of our calibration is the opposite of our error, or our relative error subtracted from 1. And then our calibration precision tells us how repeatable is this input-output correlation. So if I take a data set and then I fit a line to it, do I get the same line equation every time? Now, let's talk about least squares regression analysis. This is a process that allows us to fit a line to our calibration data. Now, why are we talking about a line? Well, first, it's the most simple way to have a calibration. I would say that in general, in calibrating instruments, you don't want to have anything that's not a line unless it's very clear that you don't have a linear relationship. So I would always assume that the input-output relationship is linear unless otherwise specified. We can run into huge problems when we overfit, when we put a 5th or 6th order polynomial into our data because it matches the data points very nicely and reduces what we assume is the error. But in reality, there's no real reason why, there's no physical mechanism why that instrument would respond using like a 5th order polynomial or a 4th order polynomial. And so in general, it's best to lean towards linear or quadratic if it has some curvature. So we assume that the output is a linear function of the input. So we have our typical equation for a line, y equals mx plus b. In this case, we're saying y equals a1 times x, so a1 is our slope, and a naught is our y-intercept value. And so if we want to minimize the sum of the squares of our error, we can follow this process to ensure that we find the line that minimizes that. So this is the line that says on average, this is the line that on average is the closest to our data points as we could get. And so one technique assumes that the best fit line passes through 0. Why would we want this? Well, it ensures that when we have 0 input, we get 0 output. Now, that is usually something that makes a whole lot of sense, right? If I'm not putting any weight onto my scale, I shouldn't be reading any weight out of my scale. In practice, that's not always how it happens. We might have some bias value that we want to be able to fix. On digital scales, there's often a tare button, T-A-R-E, that allows us to shift whatever weight the scale is reading when nothing's on it back down to 0. That would be like adjusting the A0 value to ensure that we have a 0 input when we have 0 output. And so how do we find the slope in that case? Well, we take each x input value and we multiply it by each x output value, and we sum over the all of the calibration points we took from 1 to n, and then we divide that by the square of each of the inputs summed from the first input all the way to the end. And then the second technique shows that when we have A0 equal to some value and A1 equal to some value, we're not assuming that A0 is equal to 0. We let A0 be the average y value minus A1, our slope, times the average x value. And then the way we find our slope, A1, is we multiply each of our x1s times our xi's times our yi's, and we sum them up, just like we did up here. And then we also sum over the square of our inputs, just like we did here. But then we modify that on the top and the bottom by the following terms. On the top, we subtract the number of inputs that we had multiplied by the average x value and average y value. And then on the bottom, we subtract the number of inputs times the average input squared. And so that is how we generate a line of best fit given some calibration data. And so if you'll join me in the next video, we'll show you an example.